Hello, everyone, and welcome to this new MLIR meeting. Today, we have Victor Ferrari, who is going to talk about integrating convolution optimization into MLIR. Victor, floor is yours.
So, hello, everyone. My name is Victor Ferrari. I'm a grad student from the University of Campinas, UNICAMP, Brazil. I see that Pedro Ciambra is listening in. He's also from my laboratory, the Computer Systems Laboratory. And today I'm going to talk about this new convolution algorithm that I developed along with some of my research colleagues, such as my advisor, Professor Guido Araújo. He is also here. And how it is integrated into MLIR. So we built a prototype and we integrated it into MLIR. So the talk is called Integrating Convolution Optimization into MLIR to Improve Performance Beyond Image-to-Column plus GEMM. If any of you don't know, Image-to-Column plus GEMM is the traditional way of computing a convolution in an optimized way. So most frameworks use this method for its convolution, including some MLIR frameworks as well. Some MLIR lowering of some dialects also use image-to-column plus GEMM. So I had two ways of approaching this talk. The first would be to introduce in detail how the algorithm works with all of the intricacies and details. And this would be a very long talk, and it would be an interesting one, but I preferred to take another route, which is to tell you a high-level view of how the algorithm works. I'm going to talk about some of the details, but I'm going to focus a little bit more on the implementation and the MLIR side of things and the compilation flow and so on. And if anyone has any questions about how the algorithm works in more detail, I left some resources at the end that you can look at, read, and learn more about how it works, or you can ask me at the end of the presentation as well. However, if there's anything that I say that is confusing or it doesn't explain correctly what I want to say, you can also ask me at that point. You don't have to wait until the end if there's something very if there's something very crucial that I left out or didn't explain correctly. So anyway, I think that being said, we can start this talk. So the agenda is as follows. We're going to start with a little motivation, talk about convolution, why convolution is important, and how it works. We need to know exactly what is a convolution so that we can know how to optimize it and how to make it faster. Then we're going to talk about the algorithm and more specifically how it is integrated into MLIR. This is the optimizing convolutions in MLIR section. Then I'm going to talk about the prototype that we built and the experimental results. So how we tested it and the results that we achieved. And finally, I'm going to talk about some of the next steps in MLIR that we want to take to fully integrate it into MLIR and make a contribution. So before we even get into the motivation and talking about convolutions, I'm going to motivate the overall talk. So why am I talking about this algorithm here? The answer is because it is good. It generated good results. So I'm not going to go through every single result in this table right now. I'm going to just focus on this right here. So this is the geo-mean of the overall speedup that we got in convolutions of machine learning models. So we tested these machine learning models, and on average, we sped up the convolutions in the model by 19% in the x86 architecture that we tested on, and 30% on the Power 10 architecture, on IBM Power 10. So this is a good result because we are talking about a realistic testing condition. So we are talking about full model inference. And of course, this only takes into consideration the convolutions in the model, but we're talking about the, we're speeding up not only in a random individual convolution, but a convolution in the context of a machine learning model, which is, I'd say, the most important use case for convolutions today. So let's start with some motivation. Let's start by talking a little about convolutions. So what is a convolution? A convolution is a tensor operation that has three structures: an input tensor called in, a filter set called fs, and an output tensor called out. And the way it works is that the input tensor has a height, a width, and some channels. In this image specifically, where we only have one channel, but you can see, you can think that you have multiple channels here in the input tensor. And we have a filter that also can have multiple channels, also a height and a width. And the way that the convolution works is that this filter is slid over this input tensor with a stride, and creating these sorts of windows. So a window is the projection of the filter in the input tensor. So you can see you have this 3x3 filter, and it is projected onto the input tensor, generating this 3x3 window. So each element of the filter is multiplied by the corresponding window element. So this 2, for example, is multiplied by this 0. And then every result, every multiplication is accumulated, and the element in the middle of the output tensor is computed. So in this case, we have, for example, 6 times 3 plus -2 times 8 plus 2 times 1, and then you add everything up and you get 4, which is this result of this this output result right here. So when you go to the next window, you go to the right one element, for example. In this case, the stride is 1, so you go to the right one element, and then you do the same thing, and then you compute this this element right here, for example. So this is how a convolution is computed. You can have multiple filters in a convolution, or you can see it as multiple convolutions as well. There's just potato, potato, tomato, tomato at this point. But usually in machine learning models, you have multiple filters as well. So you do this process in the input tensor multiple times, and each filter generates a different channel of the output tensor. So what I want everybody to remember from this slide specifically is that each convolution output is the result of multiplying and accumulating the elements of a filter and a window. So each output element is directly connected to one filter and one window. So this filter will be computed with multiple windows to generate multiple output elements. And this window will be computed with multiple filters as well, when the convolution has multiple filters. So this is the important part, because this is going to be an important insight for the algorithm. So convolutions are important in machine learning because convolutional neural networks are some of the most common types of machine learning models that we have today. So for image recognition, image generation, for audio pattern recognition, and computer vision and many other problems, we use convolutional neural networks, which have convolutions as their main operations. So in this case, it is important that we optimize it as best as possible, because not only that, it is also a very expensive operation. It is usually the most expensive operation on a convolutional neural network. But how do we optimize these convolutions for CPUs? So we're going to be talking about CPUs specifically today. So you can use a cache tiling macro-kernel. So a way to tile the convolution so that it fits into the cache hierarchy. An optimized micro-kernel, so a routine that uses the most that the hardware has to offer to compute as fast as possible the actual multiplications and accumulations that you want. And fast packing. So the microkernel usually does not take the tensors as they are in the beginning of the convolution. So you have to rearrange the layout a little so to use the microkernel to its full potential. So this is called packing, and we want to do it very fast because this can be considered overhead. The only thing that is not considered overhead in this entire process is the actual microkernel, is the actual computation. We want to spend as much time as possible doing the actual multiplications, right? So these three things right here are similar to how the BLAS libraries handle matrix multiplication or GEMM. They also use these three things. They also use a cache tiling macrokernel, an optimized microkernel, and fast packing. So the way that some people thought about this similarity is, well, if it's so similar, let's use the matrix multiplication routine instead of creating our own. So this created the image-to-column plus GEMM method of computing a convolution. So the image-to-column transformation takes the windows of the convolution and transforms each window into a column of a larger matrix. And then you can solve the resulting problem with a GEMM routine from a BLAS library, for example. So in this case, you have a transformation step before you get to these three things. So this is an overhead. You're creating an overhead. You're creating a transformation that takes time to rearrange everything and expand this tensor into windows and then put them into each column so that you can use something that is optimized. But if by definition, when you're using this this transformation, you're wasting time. So the best way of optimizing convolutions for CPUs is to not try to fit a square peg on a round hole, but just put it on the square hole. And that's what we did in our algorithm. So let's talk about that for a while. So this is the second section, the optimizing convolutions in MLIR section. So how do we do this in MLIR in a compiler environment? So we use three compiler passes. One analysis pass, a data transformation pass, and a lowering pass. The analysis pass is called convolution slicing analysis, and it is responsible for calculating a tiling strategy for the convolution. So it calculates the tile size and its distribution over the cache hierarchy. We're going to go into a little more detail on this analysis pass in a bit, but this is what it does. It calculates what we call a tiling strategy for the convolution. The data transformation pass is called filter packing. So if the convolution filters are static, they can be packed at compile time. We can rearrange the layout to be what we want at compile time if these filters are static, if they are available at compile time, which is a realistic assumption to make. A lot of machine learning frameworks, when they are compiling for model inference, these filters are static and they are available at compile time. So we can do this data transformation pass. But depending on your use case, it might not be. So this is an asterisk, because if the filters are not static, then you just eliminate this one. You just don't do it. And you do it at execution time. You pack the filters at execution time. And finally, the lowering pass is called convolution slicing optimization. So the convolution slicing optimization pass takes the tiling strategy computed by the analysis pass, and it generates code for it on a lower level. So it lowers a convolution operation, for example, to its implementation in other dialects, and it generates the macro-kernel that we want and all the other parts of the convolution. So let's see how these passes work in an actual compilation flow. This image will be our best friend for a while now. This is going to follow us for a few slides from now on. So we start with a machine learning model. This is the current compilation flow. You can have different compilation flows that do not start with machine learning model, but starts with individual convolutions, for example. I'm just going to go through the current one, the one that we have implemented right now in MLIR. We start with a machine learning model. We pass it through a model converter, so we have a high-level MLIR code. So the high-level MLIR code is just a sequence of operations, of machine learning operations or machine learning layers that are just converted into MLIR code. So you have a convolution operation, you have a pooling operation, and this can be, for example, the Onyx MLIR dialect. That's the one that we are using. We have implemented using Onyx MLIR, but for you can also think of it as Torch MLIR or other types of machine learning frameworks that use MLIR to convert a model directly to MLIR code. So at this point, we have all the information that we need for the convolution. So we have the convolution shapes and basically every information that we need to generate an optimized implementation of these convolutions. So at this point, we run through the analysis pass. We do the analysis pass to use the hardware information and the convolution information to generate the best tiling strategy for that hardware and that convolution specifically. So we do this for every convolution inside of our model. So it generates the tiling strategy, which is then used by the filter packing routine to rearrange the filters to the layout that we want, and by the convolution slicing optimization lowering pass that itself generates a loop nest, an input packing routine, and a micro-kernel. These three are separated because they are all important on their own. The loop nest is generic, right? So with the tiling strategy, you can generate the loop nest for any hardware. But the micro-kernel, since it has to be optimized for each architecture, it is architecture specific. So it is a different ball of wax than the loop nest, for example. And then we have the input packing, which bridges the gap between the tiling and the micro-kernel. So it rearranges the input tensor data so that the micro-kernel can have a better can compute the convolution faster. So this is why the input packing is also linked directly to the micro-kernel, which is therefore linked directly to the hardware. So it is hardware specific as well. Everything is then further lowered until you reach LVMIR and so on all the way to the binary. And then you complete the compilation flow. So now let's talk a little about some of these blocks a little further with a little more detail, but still on a high level basis. So let's start with CSA, the analysis pass. The analysis pass calculates the tiling strategy, right? So it calculates the tile size and the distribution over the cache hierarchy. So the tile size is calculated so that one tile of each type, so one input tensor tile, one filter set tile, and one output tensor tile fit into the L1 cache at the same time. So then the microkernel can come in and take these two input tiles, the filter set tile and the input tensor tile, and use them both to compute an output tile. So the tile size is calculated so that one tile of each type fits in the L1 cache. Then the two values are calculated for the distribution over the cache hierarchy, the K2 and K3 values. The K2 value is used to determine how many filter tiles fit into the L2 cache at the same time. So you maximize this value so that you can store as many filter tiles in the L2 cache at once. You also need to store the one tile from the L1 cache is also in the L2 cache, and also K2 output tiles as well. And the K3 value is the same thing, but for the L3 cache. It determines how many input tiles you store at the L3 cache at the same time, so that they can be reused. So why do we want to store many tiles in the L2 and L3 caches? Because to compute the actual convolution, we have to compute every combination of input tile and filter tile. So we have to compute 0 with 0, 0 with 1, 1 with 1, and so on for every combination between filter tiles and input tiles. So there's a lot of reuse between them. So if we can keep these tiles in the L2 cache for as long as possible and reuse them as best as we can, we save a lot of time in data movement between cache levels and between memory and cache. So now one question that you might be having is, why do we store filter tiles in the L2 cache and input tiles in the L3 cache and not vice versa? And the answer is, you can do it the opposite way. You can use it, you can store input tiles in the L2 cache and filter tiles in the L3 cache if you want. And this is called scheduling. So the scheduling is either input stationary or wait stationary, and this depends on which tiles are stored in each cache level. So in this image right here, we have filter tiles in the L2 cache and input tiles in the L3 cache. So let's go with that for now, but it can be the opposite way as well. Okay. So now that we talked about how to improve data reuse between the tiles, let's talk about how this is calculated. The tiles, the input tensor and the filters are tiled through their channel, tiled on their channel dimensions. So let's say the input tensor and the filters have 128 channels. One tile might have 16 channels. So in this case, we have multiple tiles for the same elements with different channel sets in each one. And the tile size, so the amount of channels in a tile, and the distribution, so the K2 and K3 values, are determined with an heuristic. And the scheduling order, so which tile type is in the L2 cache and which one is kept in the L3 cache, is determined with a cost model that takes the DRAM bursts into consideration, as well as all data movement between cache levels and DRAM. So this is how the analysis pass works, and this is a rabbit hole that we can go on and enter for hours if we want, because this is a very complicated part, but at a glance, that's how it works. In the end, we have tile size, so the amount of channels in a tile, and how many tiles we keep in each cache level. And we have a cost model, and the cost model determines which type of tile is kept in each cache level. And this is then used by the convolution slicing optimization lowering pass to generate the actual code, the actual implementation. So that's what we're going to talk about right now. So the way that it works is we use this abstraction of layers, which are just a loop nest. This is just a loop nest in practice. So the outermost layer goes through, iterates over the channel sets. So let's say again, we have 128 channels and each tile has 16 channels. So this outermost loop goes through groups of 16 channels. So the first 16, then the next, all the way to the final set of 16 tiles. This is the outermost loop because there's no reuse between these different channels, because they have different data. So we don't have reuse between them. So we don't need to. So it is the best way to iterate through them is after every single tile of these 16 channels have been computed. Then you go to the next set of 16 channels. So the outermost loop, and then the other loops are just iterating over all tiles. So it iterate over the input tiles and the filter tiles so that we compute every combination between them, and at the end and during this process it works the way that the analysis pass calculated it. So it keeps some tiles in the L2 cache and some tiles in the L3 cache. So this is how these layers work. And at the middle of it, at the innermost section of the loop nest, we have the micro-kernel that takes one tile of each type and calculates the output with them. So let's see how this is actually generated. What code is generated in MLIR to do this? So these outmost layers here, the layers 5 through 2, they are converted into literally one loop each. So this is literally just a loop nest that iterates over tiles. So this loop right here goes through the channel amount. So in this case, we have only two groups of channels, two channel sets. So we were using 128 channels per in the input tensor as an example. So, but a better example for this one would be if the tile had 16 channels and the input tensor had 32. So the input tensor and the filters have 32 channels. So we have two groups of 16 channels, and this is the first loop. The second one goes through groups of input tiles. So we have 3,136 tiles, input tiles in this convolution specifically, and it goes through in steps of 196. This number here, 196, is the K3, that K3 value, the amount of tiles that are stored in the L3 cache. So it goes through 196 input tiles at a time. So it reuses these 196 tiles again and again and again until everything is done. Every computation is done, and then it goes to the next group until you finish all 3,136 tiles, input tiles. The third layer does the same thing, but now with filter tiles and the K2 value. So the K2 value determines how many filter tiles are kept in the L2 cache at a time, and in this case, it is 8, which in this convolution specifically, there are only 8 tiles 8 filter tiles. So we only have one iteration of this loop right here, but you can, in a different convolution, you might have, I don't know, 32 tiles, 32 filter tiles, but K2 is still 8, so it goes through 8 tiles at a time in this loop. Then the next loop, which is layer 2, goes through, iterates over this set of 196 tiles. So 0 to 196, and so on. Then you have a bunch of code here in the middle that we're going to skip for now because it is the packing routine. The packing routine is also generated, and it is done at this point. And then you get to the innermost layers, which are just the same thing as this layer right here. It goes through these 8, the 0 to 8 with step 1 in this innermost loop. Then you have some subviews that are used, that I use to offset the memrefs that I'm using. So I need them to be on a certain offset. So I'm using subview for that. And then we call the microkernel, which is this final operation right here, which is still not lowered at this point. It's just the microkernel call. So this is how the convolution operation is lowered using the convolution slicing optimization. You can see that we use many values that were calculated by the analysis pass. So this value right here is calculated by the analysis pass, this one, and this one. And then we generate loops to iterate over the correct amount of tiles at a time. And then at the end, we offset the filter set and the output, and then we call the microkernel that will actually perform the computation of the convolution. So let's talk a little bit more about this microkernel, shall we? In our case, we use an outer product microkernel. So it is a microkernel that uses outer products to compute the convolution. And I'm going to go into a little bit more detail about it in a bit. But the thing is, it actually can be the same as the matrix multiplication microkernel. So the BLAS libraries, they use outer product microkernels for their GEMM routines. And we can use them as well. And that's actually what we're using. We're using an external library to call the microkernel that we took from a BLAS library. So we're not using a microkernel generated by MLIR yet. That's not our prototype. Uses an external library for the microkernel. But it can be the same as that, and we can also use the same microkernel as a matrix multiplication routine that follows that same pattern as the BLAS ones in MLIR, if we have them. I'm not sure. And that's actually part of what I wish to achieve here. I want some feedback on a few different parts of what I'm going to be talking about. And the first is the microkernel. So we know that there is an intrinsic in LLVM that does basically what we want, specifically for some architectures. I know that it does exactly what I want. But the intrinsic has some problems. The intrinsic is not MLIR. Yeah, would have to be. We'll have to mix and match intrinsics and MLIR. It's not ideal. And I would like to know an MLIR-centric alternative, but for now, I'm not sure what that would be. So I want some feedback, please. At
Do
the
you want
end,
the feedback now, or do you want to wait?
It's better to wait. I'm going to go back to this in the end.
Okay.
Thanks. So in this outer product microkernel, it can be emulated using any architecture that has SIMD computing, or we can, depending on the architecture, we already have outer product operations integrated into the hardware. For example, on Power 10, IBM Power 10 has the MMA engine that uses outer products implemented in the actual CPU as an ISA extension. So, but it can be emulated in different architectures. So I'm going to start by talking about it with using outer products that are hardware implemented, because it's simpler. But you can just keep in mind that if we don't have this implemented in the hardware, you can just emulate it, and it will be the same thing. So how do you calculate a convolution using outer products? So the way that we do that is by vectorizing it. So if you recall, I said at the beginning that each convolution output element is the result of computing with one filter and one window. And outer products are very great operations because they are very dense. You start with 2n elements. So for example, n is 4, so we start with 8 elements, 2 vectors registers of 4 elements each, and you end up with 16 elements in the end. So it is a quadratic expansion. You start with 2n and you finish with n squared results. But in this case, you have to do multiple outer products and accumulate everything on top of each other so that you can fully calculate every single term of this of the output element. So in this case, you can see that in this case, it is similar to doing it normally, to doing the convolution normally. So you multiply A with 1, and then B with 2, and then C with 3, and so on. And then you accumulate everything and you get one output element. So each output element is the result of many different outer products. But the outer product can be used to vectorize it. So instead of doing it one output element at a time, we do it 16 at a time. So we do it with 4 filters or kernels. I have K here, but it's filters. So we start with 4 filters and 4 windows, and then you get 16 results with every combination between filter and window. So one outer product does one partial result of every of these 16 elements. And then you accumulate multiple outer products on top of each other for all of these elements of the windows and filters and for all channels. And then you get a full convolution output. So this is how we use a microkernel, an outer product microkernel, to compute a convolution. So the only thing that we actually need from the microkernel is a microkernel that can read from memory sequentially and do accumulation of outer products with the result. That's all that we need, and that's all that the BLAS library microkernel does. And and all the rest, the access pattern, we use packing to make it to rearrange the layout of these windows so that they are sequentially in memory, so that the microkernel can just read and compute the result. So the packing layout is as follows. We pack the first element of each window and then the second element of each window all the way to the final element of each window. In this case, we're talking about 16 elements because our input tile has 16 windows on them. So imagine that we have a tile of 16 windows and we want to pack them for the microkernel. We do it like so. We take the first element of each window, then the second one, all the way to the final one, and for all channels as well. This is I'm omitting the channel hits here in the images for simplicity. Now, there's a useful observation that we can use to make it so that packing is faster. That we can implement faster packing using this observation when the stride is 1. As you can see, when the stride is 1, you start with this window right here, and then you go to the right and takes the second window, the dotted one. And the first element of the second window is the second element of the first window. This is a very useful observation because in this case, if we have the first element of each of the first 4 windows, so we have, let's say, this is the first element of a window, this is the first element of the second one, the first element of the third, and the fourth, and we have these elements here in this vector register. If we shift this register to the left, and then you add a serial in element at the end, you get the second element of each window. You get the second element of the first one, the second element of the second one, and so on. And how do we do that? We can use an assembly operation, an assembly instruction that is available on many architectures that concatenates 2 vectors and then shifts the result to the left. So this image here is from the power VSX instruction, but x86 has the same thing, and other architectures also have the same thing, ARM, and I took a look at MIPS as well, and it also has a similar instruction. So we call this vector-based packing. So we start with 2 vector registers, we concatenate both of them, and then we shift the result to the left by 4 bytes, and then this single precision element goes out the window, and you take the other 3 elements from the first vector register and the first element of the second vector, as well as a serial in element at the end of this vector. And this can be implemented in MLIR using the vector dialect without using assembly directly. This can be done using the shuffle instruction. So the shuffle takes 2 vectors that you can it concatenates them, and then you can use a mask to shuffle the elements and take whichever elements you want from these 2 vectors. So you can take elements from 0 to 7 in whatever order you want, and you and add it to a different vector. This shuffle instruction, written just like this, is lowered to this instruction right here. So I tested it, and it does what we want to. It lowers to the correct instruction, at least on power. I haven't tested in other architectures. But there's just one problem with this, and it is that the vector dialect, it uses virtual vectors, but if you want everything to work smoothly with the assembly instructions, you have to make the virtual vectors to be exactly the same size as the physical vectors. At least that's what I read on the website, and what my experience also showed, that you need to actually create 4 element vectors if your hardware uses 4 element vectors. And this can be a problem when we're talking about different architectures, such as AVX 512 that has 512-bit vectors in vector registers instead of regular 128-bit vectors. So we would have to probably have a different implementation for that, or not use that extension, which would be possibly be a waste of performance. So in this case, you load the elements, and you have to store them again and again, because we have overlaps between windows. This is actually, I forgot to talk about that. We have overlaps between windows, so this element right here will be stored multiple times. So this is why the shift instruction it improves performance, right? Because we would have to read this again from cache, but instead we can just keep it inside the register and just shift it to the left, right? So you have data replication when packing. You're packing the same element multiple times. So you can just read a vector once and then just keep shifting them and storing them again and again to save on memory reads or cache reads. Okay, so this is what I wanted to talk about, the actual algorithm, so how it works and how I implemented it so far. So let's talk a little bit about some results.
Vincent,
So,
just a time check. You have less than 10 minutes, right?
Okay. What? Sorry?
So it's just a quick time check. You have less than 10 minutes.
Okay, it's very quick. I think this took longer than I expected. Sorry, but 10 minutes is enough. So we tested it on two architectures: IBM Power 10 E1050 CPU and Intel Xeon Silver 4208 CPU. This one has AVX 512, and this one has the MMA matrix engine. So we took 100 measurements with low variability between them, and we used the Onyx MLIR environment for full machine learning model inference. And we measured against the Im2Col plus the OpenBLAS GEMM routine. So as you can see, these are the results. We're back to them. For these machine learning models, we have convolution speedup and model speedup. So the model speedup is the end-to-end inference time and how much we sped that up, and the convolution speedup is talking about only the convolutions of each model. So you have on average 19% on speedup on convolutions in x86 and 30% on Power 10. While end-to-end inference, we have on average geomean 15% on x86 and 18% on Power 10. So we are speeding up machine learning model inference by 18%. And this is using Onyx MLIR, which is still in development. So the other operations are not that optimized yet as well. So for example, on Power 10 in VGG16, convolutions are only responsible for 40% of the time share. But for individual convolutions, we achieve better performance in 90% on both x86 and Power 10, and up to 92% speed up and 111% speed up on Power 10 and x86 respectively. Why it works? Well, we eliminate the image to column transformation. We don't need it, and we're doing packing faster. So in this case, we are reducing cache misses by quite a significant amount. So it goes from 18% or 16, 17% on average in the baseline, and SCONV, which is our algorithm, it falls to like 10%, 9% of the loads result in L1 cache misses. And this difference is exacerbated in L2, but the percentage is lower, so it's not an apples to oranges is not an apples to apples comparison, but it also lowers a lot proportionately. And you can see that we have many packing improvements, right? So especially on Power 10, because the micro-kernel is faster on Power 10 because of MMA, we have in general like 40% of the time is spent on packing on the baseline, and like 10% is spent on packing in our method. On x86, it keeps that 10% on our method, but the baseline is a little faster. It goes to like 30% or of the time is spent on packing. Now, finally, the next steps. We want to contribute this project to MLIR. So we have micro-kernel lowering and macro-kernel lowering. The micro-kernel is implemented as a separate library, and I want some suggestions. I want some feedback on it. So as I said, we have that intrinsic. The problem with the intrinsic is that we have to load everything to vectors, and then this generates a spilling problem when calling the intrinsic. And or we can have an MLIR-centric alternative, which would be the ideal solution. And the macro-kernel lowering today, we are lowered from Onyx dialect to Affine, memref, vector, and arith dialects. And we want some suggestions because where is the best fit for this sort of convolution algorithm? So linalg has convolution has a convolutional operation with many different layouts, including the NCHW layout, which is our layout, the one that is used in our algorithm. Or we can implement it in Torch MLIR, or somebody in the Discord talked to me about this and suggested a TOSA, but it does not use the NCHW layout. It is NHWC layout, which is not viable for our algorithm. For more information, you can go through the archive that we have this paper that is actually, we submitted to a journal, but the preprint is available at the archive at the link on screen right now. And this work is based on the efficient tensor slicing for multiple core NPUs using memory burst modeling work that was published in SBAC PAD on 2021 by Rafael Souza, which is also my co-author on this paper. I wanted to go a little bit more through the code. I have the MLIR, a model that is completely lowered to the we can see with a bit more detail how the algorithm works in MLIR, but I think we don't have the time for that. So I'm just going to say thank you. Any questions?
Oh, thank you, Vincent. Let's move on to question. I know Nicolas had one during the talk, so maybe we can start with this one. For everyone else, you can ask on the chat or just unmute yourself. I think we have, I don't know if there is a raised hand in Zoom actually, but yeah, let's start with Nicolas maybe.
Okay, great. Yeah, thanks a lot for the great presentation. So I think you had a few questions in your presentation. I also have a question for you. So maybe the question for you is, could you go a little bit again over the packing? Because I am not completely clear how the packing works. So I think you mentioned you're using NCHW, and I think I heard copying the same element multiple times.
Yeah, all right.
So are you doing a sort of Im2Col on the fly, or is it not an Im2Col on the fly?
If we want to use another product, micro-kernel, we will kind of need to use some sort of data replication. We will need to do computation with multiple windows at a time. So, and if we're doing it with consecutive windows, then we will have data replication. There's because the micro-kernel just reads sequentially from memory, right? So there is overlap between these windows. I wouldn't say that we're doing image to column on the fly. We are doing, because we are combining the what you would usually call the image to column transformation, which is the expansion of this input tensor into windows, and the packing that happens inside of the GEMM operation, the GEMM routine, right? So the packing routine of the GEMM operation also does other types of layout changes. We are combining both of them so that we can do it at the same time. and we don't have to materialize a large matrix. We only need that one tile at a time, to pack one tile at a time. So
right, but the amount of data that you use for one tile, is it exactly the size of one tile? Is it a little more, or is it 9 times the size of one tile because that's what the Im2Col thing does, I guess, or maybe something in between?
Yeah, it depends on how you define a tile. We define a tile as a number of windows, right? So in our case, it is the exact size of one tile. But if you want to say, if you want to talk about the comparison between the elements that we use in the tile, the size of the tile, and the size of the input tensor, yes, we're using, in the case of a 3x3 filter, we're using 9 times the amount of memory, but for one tile. Okay. At a time. We don't construct a huge matrix, which is 9 times the size of the input tensor.
It's you take a slice and you copy that slice 9 times in some local memory. You have the space. You don't have huge memory traffic. And okay, yeah. So okay, so that's interesting. So I kind of view this as maybe I would call it Im2Col on the fly. But we can take it offline. I don't want to take too much time, but it's certainly interesting, and especially the performance that you get. I would just mention maybe one thing that may be interesting is that there's one implementation in MLIR that does, I would say, vectorization at the convolution level for a 1D conv. It also uses an outer product. However, it uses it by kind of extracting a vector out of a bigger vector and sliding it. So it's actually not copying more data, but it's just taking, let's say you have a vector of 16, it computes, the result is 14. And so you're going to take elements 14 from 0 to 14, from 1 to 14, and from 2 to 14, and these become vector outer products. I mean, we can go in details offline, but there is also a outer product based implementation, but it is different in that it's actually a 1D conv. But okay, anyway, thanks. That's really interesting. Yeah, we should certainly follow up. I would say at the linalg and tensor level, you have the facilities that you would need to basically reuse implementations and plug in new things. So that's the level at which a lot of these things are built today. Okay. So I would encourage you to try that. I'm happy to help. On the vector questions, so we do have lowering to vector outer products and lowering to LLVM matrix intrinsics. They just need to be activated, but I'm happy to show you how.
Okay, thanks. Yeah, I would really enjoy that.
Cool. So yeah, let's follow up, I guess, on this course or something. And yeah,
I want to write about it on Discourse as well.
Okay, cool.
Amazing. Thanks. We are out of time. Maybe we can take one more question if anyone has something to ask. And otherwise, Discourse will be a great follow-up to see how we can maybe integrate this or what to do, what components we can learn from this, and how to move forward. I don't see anyone unmuting themselves, and there's no message on the chat. So I think we're gonna just leave it there for today. Thanks again, Vincent. Great talk. And I look forward to your follow-up on this course.
Okay, thank you. Thank you for having me. If anyone wants more information, the links are on the screen right now. We have our paper that we just wrote, and we have the previous work for NPUs.
Awesome. Thank you.
Cool.
All right. Bye, everyone. See you next time.